Hello. Today we're going to discuss finding the derivative of integrals with functional bounds. This means there's a function in one of the two bounds. Sometimes there's one, sometimes there's two. We're going to talk about both cases and some other weird cases too. Okay. The fundamental theory of calculus states this is actually very important. This is the main focus of our lecture. The fundamental theory of calculus states if f is continuous on closed interval AB, which means A and B are both included in that interval, then big F of x, which is defined as this integral, is continuous on that same interval and is differential on the open set AB, which means A and B are not included. And its derivative is just f of x, which is written down here. Big F prime of x equals this f of x thing. The second thing is if f is continuous over a closed interval A and B, and f is any antiderivative of f, then the integral from a to b of f of x is this big F b minus big F of a. These are very two crucial points. We're going to focus more on the second point today, just to show you a fluid, correct method for every single example that they could ever throw at you. There are other important integral rules I want to talk about. These are not essential to what we're going to talk about today. As you can see, we'll skip past a lot of these rules, but they're really good, important rules to know. The first one is that if you want to flip the bounds, you can. So you're going to add a negative to the outside of the integral. And say I had a value b in between a and c, then I can split up this integral from a to c this integral from a to c to two different integrals, a to b and b to c of this function. Again, these aren't going to come into that much in play because, well, you're going to see why. But I think they are very important just to talk about. Anyway, here's our first example. Let's scroll down a little bit. Here's our first example. First off, the first thing you're going to do is look at the bounds. Now, you don't have to do this step technically, though I would suggest always trying to look at the bounds. What you really want to see is you want to see if you can use the first fundamental theory of calculus, which, again, it's very important here. You notice the first fundamental theory of calculus states that your derivative has to be a to x. If you want to use that, you want to make sure there's a function on top and a value, number value on the bottom. We can use the second theorem if we want, but especially in this case, it's very nice to. So I guess first optional step is that. The next step is actually very important to find f of t. So in this case, f of t is whatever's in the middle of your integral. So right here, it's going to be cosine of t. Then after this method, I'm just going to plug in our f of t to our integral. Let me center. I'm going to do it a little more. So it's all derivative here. So 0 to x, but now it's f of t. And in this case, we're going to define big F of t is basically the integral of little f of t. This is going to be very important because now what we're going to do is use the second theorem, or second part of the fundamental theorem of calculus. This basically states, I'm reusing it in a different way, I guess, in a weird way, but it's AB of f of x equals big F, big F, B, big F of A. So in this case, B is a function x, A is your function, like your letter 0. So we get the following. And now I take this derivative. Note that since big F is the integral of little f, the derivative of big F is little f. This is due to the second fundamental theorem of calculus right here. If you notice that. So this derivative is just f of x. Now, this is interesting. This is big F of 0. This is a number because we've put a number in the function. So it's not a function anymore, it's a number. And we all know the derivative of a number is just 0. So we're left with this f of x minus 0, which we know the definition of f of x is just cosine. The right answer is just cosine of x. Now, you might be asking, okay, why did we do all the steps? The first fundamental theory of calculus literally just states the exact thing we were looking for, right? The derivative is this f of x thing. It's the exact same thing, right? Because the number here is a, x is right there. There's a function, f of t. You take the derivative of that, you get cosine of x, which is what we said we would get. Uh, because sometimes things get a little funky. Let me show you what's wrong. So let's do question 2. So question 2 is going to be this derivative. By the way, unlike last time, uh, these are problems I made up myself. Um, YouTube has a weird thing with links, it seems like. If you're a new account making newer videos, they don't like if you put links in it. So I will tell you when I'm able to put links back in, but right now I'm unable to. It's weird. I don't know why. They don't trust me to put actual resources in there, but whatever. So I made these up myself. Um, First thing we're going to do. The bounds are already pretty good, so I'm just going to define an f of t like before. And we're going to write it down. The integral like so. Then using the second fundamental, or the second part of the fundamental theorem of calculus, we go write down our answer. There we go. And now when we take the derivative of this is now not just little f of x, because there's another function in here. Last time, the function was x, so the derivative of x is 1. Now we can't do that. The derivative of sine x is not 1. So in this case, we're going to actually take the chain rule of this function. Now, it's not that bad. All you got to do is regular chain rule steps. So remember, chain rule is, let's write it right here. It's just this. So using this, our big f of x, turns to little f of x. That's our definition of our big f of x. Our function g is just sine of x, so we're going to keep it the same. Then we're going to multiply it by cosine of x. And then this is still 1, because that is still a number, so that's still 0. The last thing we have to do is define plugging back in for f. So in this case, f was 3t squared. So our answer is going to be make it a little more clear, because it's not really just this. So this is why we don't just use the first part of the first fundamental theory of calculus. It does work for the first question we did, but for many other questions, it does not work. Or for some other question, it doesn't work. So we're going to try to stay away from it. Number 3. Okay. Now here is what I was talking about when we say checking bounds. You can just do the regular method where we do what we just did, but I find it a lot easier to change the bounds such that there's a number on the bottom and something on the top. How are we going to do that? Easy. Use that one of the rules that we already knew. So remember our rule that says this. We're going to use this to our advantage. So our ddx stays the same. I will now add a negative here. Our bounds will now switch. And now we get the following. Now, you don't have to do this. However, as problems get more and more complicated, I always think it's just easier to get that out the way and to make it the same each time. you will see in some problems it gets very messy. On the problem we're going over today, the basically the starter problems for this unit, uh, you don't see it that much, but things can get very complicated very quickly. Anyway, now we do the same steps. Our f of t is this. Let me spread it a little bit for you. Our d to the x, our thing is now this. And then we take the integral like we always done. There's still a negative there. Our integral is going to be big F. It's going to be big F of 0. I'm adding this negative already in there, so the first one's negative, the second one's positive. This derivative is going to be similar to the same thing. I'll remember the derivative of tangent a secant squared. And then this is still 0. So this is our final answer. I should plug in F. F was, I believe, 1 plus x squared. So we get this. Oops. Oh, I believe I just... Well, it looks like I've accidentally closed it. We were at the end, but the idea was, let me just write it out, I guess. The answer was going to be this. Which, this is a good final answer. We're done here. I did want to say, oopsie. Well, that's cool. I didn't know this was a thing. Interesting. Anyway, this is the answer to the question that just showed. This is actually very funny. Well, it's actually negative here. There's something funny going on. This thing here, I don't have to know this, but it's a good thing to keep in mind. This is just secant squared of x. So something I like about this problem and why I chose it is because this derivative is that this whole thing is just -1. I thought it was a cool little thing, so I chose, or I made it fun. I have two more I want to go over. Just run a little more. Now here we have two bets. Now I'm going to show you. There are two ways you can do this. There is a way where what you do is you define a number a that's in between both x and e to the x, and you split the integral up into two parts. We're going to go the fast way because it's a little easier, I think, to understand. Anyway, same thing as before. F of t is this sine -1t. So then our derivative looks like this. You have your the following, and then we take its derivative, or this integral. The derivative stays where it is. And then we take the derivative, which is very simple. Remember chain rule, dx times e to the x. Remember the derivative of e to the x is just e to the x. And this is just regular f of x like before. And then we get a value f e to the x. That will be, I believe it's sine. Yeah, okay. It's going to be this. And that'll be your final answer. Now, I think some people, some astute individuals might have noticed, hey, the answer here, I guess I don't have it because my Zoom looks funny, but the first couple of questions, remember this one, let me write it out again. The derivative was this. So all I did, realistically, was put this in where the t is, and then I took the derivative of tan squared and multiplied it by it. And that's the correct answer. And that works for these problems. When there's two, you do a similar thing. You take sine, you put your top up in there, take the derivative of that, like so, and then x, same thing, right? You don't actually have to do all this hullabaloo. So why am I doing it? There are shortcuts. Because problems like this. This is a very tricky problem. I have this down in my notes. So I took notes in Calc 2, or it's Calc 1 when you learn this. So in Calc 1, I took notes. And I saw this and I thought this was a really cool example. So here, rounds look great. No funny business. And so we're just going to take our procedure and keep going with it. So our procedure is the following. There's the other arrow. Now remember, there is this x here, so it's going to be a little more funky. But we're going to do the same thing we always do. It should be x squared, I believe, right? Yeah, okay. Now what we're going to do is multiply each of these by x, distribute the x. Oops. There we go. Now, this is very interesting. Let's scroll down a little bit for you guys. My apologies. This is very interesting. Because what we have here is now the derivative of this is just f of 2. It's not 0 anymore. It's actually going to exist. And this is now a chain rule problem. Or it's not just a chain rule problem. It's a product rule problem. Do you remember product rule from Calc 1? Which actually is in, but earlier in Calc 1, you have something like this. You have two functions, and you want to take the derivative of them. You get this thing. So what we're going to do is do that with the first one. So let me actually scroll up a little bit so you can see the first one. So the first one's going to be, let's make f of x x, g of x big F x squared. So our first derivative is going to be big F of x squared plus x little f of x squared times 2x. And now this part is now just f of 2. Now, this is funky. I have this f. I'm going to plug in that f. I'm also going to simplify this equation. And I'm going to move this over here. You're going to see why in a little bit. Let's do all the things I just said. So first, move the big f's along. We get what 2x squared times whatever f of x is. F of x in this case is our sine. So we get, oh yeah, it's sine of, it's x to the fourth in this case. Because it's sine x squared. And then we're plugging in, and wherever time we see an x, we plug in an x squared. So it's x squared squared. So that's x to the fourth. Now, what do I do with this? Very interesting concept. Remember, this is a definition of an integral. Since this is a big F is the integral of little f, this is now the following. And that's going to be the final answer. You don't have to take any more integrals or derivatives because there's no derivative over here. And actually, I should probably plug in what x or ft is. Let's do that. This is actually not a possible integral, I believe. Or it's not a very easy integral. So I suggest you do not do that. When I took this class, I didn't have to. At least my final answer was not, and that's so I assume you wouldn't have to either. And there you go. I wrote it down. There we go. There we go. Okay. And that's why I wanted to teach you this method because it goes through basically everything you need to know to take on these much harder problems. So sometimes you will get problems this difficult, and you can't just do the quick, easy method. You have to actually go through a lot of these steps that are a little more complicated, a little more tiresome, but they will get you the correct answer every time. Um, so yeah, that was our lecture today, I guess. Thank you all for showing up or coming or watching, I guess. You can tell I'm a TA. Thank you for watching the whole video. Please tell me in the comments if you want me to go over any topic specifically, from high school to graduate school. Let me know. Um, and yeah, please stay curious, stay alert, and most importantly, try your best. I will see you next time. Where's the